My name is Alyssa Wilczynski, and this presentation was co-written by myself and Heng Li, another optical engineer for Zemax. And today we're going to talk about scattering and source libraries, as well as the general scattering and source models available within OpticStudio, and how to choose between them. So in this webinar, we'll start by identifying the difference between surface and bulk scattering. We won't concentrate on bulk scattering for the purposes of this webinar. We'll then go on to look at the available surface scatter functions and define what it means for a scatter function to be anisotropic or isotropic. Once we know all of the available scatter types, we'll look at when to use each one that's available, and then take a look at a few tools that are available as well for identifying the differences between scatter profiles and seeing what the scatter output is going to look like. Then we'll move on to talk about sources and look at some of the available source models, as well as the libraries that come with OpticStudio Premium. That's for the Radiant Source Models and IES Source Models. And then we'll take a look at a few tools for visualizing those source models. And finally finish up with steps on what to do when you need measured source or scattered data. At the end, we will have a Q&A session. So you will have opportunity to ask questions at the end of the webinar, but there will be no questions during the webinar. So again, my name is Alyssa Wilczynski. I'm currently the Engineering Services Manager for the US. And previously I was an optical engineer at Zemax. I was also the primary engineer responsible for constructing the measured source and scatter libraries that we now have in the premium version of OpticStudio. And I was the Western Regional Sales Manager for Radiant Zemax, basically for the side of the company that's now known as Radiant Vision Systems. So I worked extensively with the products that are used to create some of the measured source and scatter models. Within scattering, we have two types of scatter, bulk and surface scatter. And surface scattering is really meant to mimic the surface roughness of any object, really, or to model the behavior of a thin diffuser. So scatter models are often applied in conjunction with a coating in OpticStudio. So the surface scatter will indicate the direction that rays need to take after they interact with that surface. And the coating would indicate the amount of energy that should be reflected or transmitted or absorbed at the interface. And rays can scatter in reflection, transmission, or both. Both is possible when you're using the non-sequential mode, which is primarily what we will concentrate on. Bulk scattering, on the other hand, helps us to model impurities or inhomogeneity inside a medium. So some examples of this would be light scattering in the atmosphere due to water vapor or droplets. There's also scattering in biological tissues that can be modeled with a bulk scatter. So essentially how rays are deviated as they propagate through a medium. And much like surface scattering is often combined with a coating, bulk scattering is usually combined with an object material. So the object will have some index, some material, some dispersion, and then it can also have this bulk scattering behavior. Both of these scatter models are best used in pure non-sequential mode. There are some exceptions to that rule, but they are best used in pure non-sequential mode. And for the purposes of this webinar, we're going to concentrate on surface scattering. Some of the built-in scatter models include a Lambertian scatter model, which means that the scattered ray has an equal probability of going in any scattered direction. So Lambertian is commonly used for modeling surfaces like a flat painted wall or a piece of paper, something that has very little sheen, and it seems to spread light pretty evenly. There's no glossy spots. There's no discernible pattern to the material. Gaussian scattering, on the other hand, has a Gaussian distribution on the projected plane, and it has an S coefficient that the user can define, and that S coefficient describes the steepness. It's a sigma value, but it essentially describes the steepness of that Gaussian distribution, so how narrow the distribution is or how wide it is in space. And the Gaussian distribution can be used for approximating surfaces that have a light sheen, but not a full gloss. So this would be something like, what's a good example? Like the surface of a table for your average kind of desk table. The ABg scatter model allows input values of A, B, and G coefficients. And there is a mathematical function associated with this model. So the user supplies the coefficients, and then we apply those coefficients to the mathematical model, and it results in a certain distribution of light. Most of the ABg models are used as a fit to experimental or theoretical data. And they're often used for modeling polished surfaces, like polished glass. We also have DLL scattering, and there are a few built-in DLL scatter models for particular types of scattering that are common, such as Mie scattering. And DLLs can also be written by the user, so if you have a mathematical function that you know describes your scatter output, you can write a DLL and use that within OpticStudio as well. As an example, we do have an ABg scatter system, and this is found in your My Documents ZMax samples folder under non-sequential scattering, ABg scattering surface. So again, ABg scatter is often used to model polished optical surfaces and housing materials. ABg is usually a representation of scattering that's a close estimate. It's not necessarily measured data, but more used as a fit to measured data. So let me go ahead and pull up OpticStudio here. Okay, so within my ABg scattering surface sample file, I can see that I start with a source point that's emitting a ray of light. It comes and it hits my rectangle, and then at which point the ray is both reflected and scattered into multiple directions. And then we are going to go ahead and look at the output on our detector rectangle. In this particular file, we actually have two detector rectangles. You'll notice that one is given a comment that it blocks the specular path, and the other is set up to show the background. So the specular path is going to have a lot of the energy in this particular case. So we block that out in order to see the remainder of the scatter distribution that's happening thanks to our ABg profile. Let's take a look first at our rectangle and see what the scatter model applied looks like. So go ahead and click on your rectangle and open up the Object 2 properties. And then go to Coat Scatter and scroll over to the right a little bit there. And you'll notice that we have a scatter model of ABg. And then our number of rays is 5. So for every one input ray, we're going to have 5 resulting scattered rays. So the energy of the input ray will be shared between those 5 output scattered rays, and their directions will be determined based on our scatter profile, which in this case is our ABg example. We do have tools within the software for modifying ABg files and editing them. So if you are interested in doing that, we have an ABg Scatter catalog, and you can also add and remove items from the catalog. So by simply changing the data within the catalog, you can save as a new ABg profile. I'm going to go ahead and close up the Object2 properties. And let's take a look at some of the tools that are available for analyzing our scatter output. So some of these are our scatter polar plot and the scatter function viewer. I'm going to go ahead and make these a little bigger so we get a better view of them. So the scatter function viewer shows the BSDF, which we're about to talk about, and the magnitude of our scatter vector. And you'll notice that as we change our input settings, so even if our scatter model remains the same, if our input alpha x changes, then we see a change in our resulting BSDF. Personally, I prefer the scatter polar plot. It's a very visually intuitive plot about what your scatter function will do. So this operates just like our detector polar object in non-sequential mode, which allows you to see data in angle space as though it were projected onto the surface of a sphere. And in this case, we can see that our resulting scatter is concentrated about this 45-degree point. And we can see that the setup incident angle is 45 degrees. So the ABg profile that we're looking at does have a high component of the light centered about the specular ray path. And I can do things like change my incident angle and see how my output would change. So if I change my incident angle to 60 degrees, I can see that that spot follows suit, following that specular ray path up to a 60-degree angle. And then, of course, the last way to look at your scatter output is to try it out in your non-sequential model. So right now, we are set up to show our detector this consider setting. Means that we're going to look at the setting in our non-sequential editor as to how we want to display the data on our detector. So if I scroll over to the right on my detector rectangle, you'll notice that we have data type 0 and color 2 for our detector rectangle number 4. So each time, and then we also have this setting here, detector color pixels by last analysis in our layout. So each time we retrace rays, we're going to see the detector fill in according to the distribution from the last analysis that was run, the last ray trace. And the color 2 setting indicates that we're going to look at false color data. Now currently this looks orange just because I happen to be highlighting this row in my editor. If I change back, we can again see that data populated. So what if we change our rectangle so that it's no longer an ABg scatterer? Let's go ahead and try a Gaussian scatter model. You'll notice by default it set this scatter fraction to 0. If that happens, you won't see any scattering. So this is essentially a percentage of the incoming rays which are expected to undergo scattering. So in my case, if I expect all rays to scatter according to a Gaussian distribution, I want that scatter fraction to be 1. And then this sigma value we talked about earlier. So first I'll go ahead and just check out what happens with a very small sigma value. Now if I run a ray trace, So analyze, ray trace, and move it clear and trace. What we see is very little light. Actually, let's double check. So let's open up our detector viewer just to be sure. So remember, we have one detector blocking our specular path. So this one just has 1 pixel by 1 pixel. It's getting a ton of light. We can see that it's getting 5 million hits. And then if we take a look at our other detector, our main detector, looking for that scatter behavior, we have 0 hits on that detector. So essentially with a very, very small sigma, our distribution becomes more and more and more akin to the specular path. So we essentially have almost 0 scattering with this setting. So back in my object properties, I'll go ahead and change this sigma value to something like 0.2. Now if I take a look at my shaded model, we can see that I am getting some scattering. If I update my layout, I'll see different scattered rays each time. And if I run my ray trace, I should see a true distribution of the rays. So note that as your sigma value gets larger, the distribution of light in space gets larger as well. So if I go up to a sigma value of 3, we'll see that light may not even necessarily always hit my detector. It can be spread out extremely far, and we see that larger distribution. BSDF is a really general way to describe the scattering of a system. We do have a few knowledge base articles that go into BSDF and the data format that we use within OpticStudio. BSDF is basically just a function that describes how much energy is going into different parts of space as measured relative to the specular ray. So the most important aspect of using BSDF data is to remember that it is enumerated relative to the specular ray path. So anytime you're looking at a particular angle, like polar and azimuthal angle in space, that needs to be measured relative to where the specular ray would have gone. This is not always the case for all measurement systems. So some measurement systems will output data with some other fixed reference. But in order to use that data in OpticStudio, you would need to convert your data from a fixed reference to this relative to the specular ray type reference. BSDF is our most general scatter format. The rays can take on any profile. And it also allows for isotropic or anisotropic modeling. And we'll talk about that in a minute. So isotropic scattering is when you see no change in your scatter profile based on the orientation of the sample. So if you were to shine a laser pointer at a transmissive sample that scatters, and you were to rotate that sample in front of the laser pointer and look at what happens to the laser pointer as it reaches a wall behind the transmissive sample, you would see no change by rotating that sample. However, an anisotropic scatter profile is when rotating that surface or that scattering object does have an effect on the output of your scatter profile. So a good example of this, which I've shown here in images, is a 60 degree by 10 degree diffuser. This one in particular was made by Luminate and is included in the OpticStudio scatter library that we'll talk about in a second. And this model is an example of anisotropic scattering. So based on the qualities that the diffuser has, when you shine light through the diffuser, depending on the orientation of the diffuser, that cylindrical or elliptical, yes, that elliptical pattern would rotate at the same rate along with this sample if you were to rotate the sample. Other examples of anisotropic materials would be brushed metals. I think that the backs of CDs have some very fine structure to them, and they exhibit anisotropic scattering. But anything that has usually items that have an asymmetric scatter output will tend to be anisotropic in their behavior. So this IES Scatter catalog is a set of measured scatter models that's provided with OpticStudio Premium. And we have essentially an online library that you can access through the OpticStudio software and download a measured model at any point. And the ISX file can be used directly within your system. So if I take a look in my OpticStudio session, under Libraries, I have my IES Scatter catalog. Oh, and I didn't point out last time, but the scatter function viewer and the scatter polar plot, which were already open in the sample file, happen to be in this section as well underneath the Libraries heading. So within my IES Scatter catalog, I can look for a particular manufacturer. I can also look for the type of measurement lamp, which in the case of the systems that we have is pretty universally a halogen lamp, although if you were to receive measured data from outside of OpticStudio, that could be different. And then you can also search by file name. So in the example that we'll do here in a minute, I had downloaded a generic powdered black steel profile. So this was a piece of steel coated with a powdered black spray paint. And then we measured the scatter results from the reflections off of that powdered black steel. So how do you choose which scatter model is going to be appropriate? ABg is best for smooth isotropic fits to data where the energy peaks near the specular path. So I don't believe that ABg is very suitable for situations where you're looking at an asymmetric distribution. It's definitely not appropriate for anisotropic scattering. And I believe that the energy peak always needs to be near that specular path. I haven't seen ways to produce ABg profiles where that's not the case. BSDF is a great option if you have precise measurements. So this could be, when I say angular measurements, what I really mean is in polar and azimuthal angles relative to the specular ray path, if you know how much energy goes into those various polar and azimuthal angle combinations, so essentially into the hemisphere or sphere about the specular ray path, then BSDF can be a great option. It does allow for anisotropic scatter modeling, and it also allows for asymmetric or unusual distributions. So when your scattering peak is not centered about your specular ray, BSDF is going to be a great option for you. And then we also have the imaging sphere, the ISX files. So the ISX files are great if they're available. If it's not available, but you still have measured data sets. So you maybe measured it from a different vendor. It's not already in the correct format. Then that's where the BSDF will come in. So BSDF is sort of a close second or a great alternative to the ISX file. If you don't have measured scatter data and all you have is really an estimate of the scatter behavior, there are a few options available for you. Probably the most likely that you'll use would be the Gaussian or Lambertian distributions. So here I've shown two different Gaussian distributions with different sigma values. So you can see how changing that sigma value either narrows or broadens the distribution. And the Lambertian distribution requires no user input. It is always fixed. And ABg is another possibility, though guessing at the coefficients could be a challenge. But if you know generally what your output should look like, you could do a rough estimate of those A, B, and G coefficients and see if you can get close. So I just wanted to talk a little bit about how we would apply this and show applying that powdered black steel profile to the barrel of a telescope. So I've got a sample file to share. We do have a knowledge base that talks about how to perform stray light analysis and uses this sample file, although I don't believe that it includes the ISX scatterer. Instead, I think that it just starts with a mirrored barrel instead of a scattering barrel, though I do believe that a scattering model would be more realistic. So the stray light system is probably converted from sequential mode. So in this case, the system is actually working in mixed sequential and non-sequential modes. My layout plots are a little confusing, I know. My 3D layout on the left-hand side is actually showing green and blue rays, which are my on-axis and slightly off-axis field points from sequential mode. And we can see that that light is coming to focus on our detector plane. So you can think of that as the light from distant stars, which we do want to focus. And then my red rays coming in are an off-axis source at a 2-degree incident angle that we want to avoid getting to our detector. And then in my shaded model on the right-hand side, I've enabled splitting and scattering of those rays. So you can see that once we allow for splitting and scattering, we get just tons and tons of ray paths within the system. And then in order to model the object, we've got our cylinder pipe. So our outside cylinder pipe is where we will want to apply our scatter profile, and we'll want to make sure that it's set up to realistically model that true behavior of whatever it would be coated with. In this case, we're going to say it would be powdered black steel. So my cylinder pipe, it's right now noted as a mirror material, and that is okay. Basically what happens is if you have a mirror material and no other coating, when you go to apply the scatter function, if it doesn't have its own energy allocations as to how much energy is reflected versus how much should be absorbed, then we're going to fall back on the idea of a mirror coated with aluminum. So it won't have necessarily 100% reflectance. So let's take a look at those object properties. So under my coat scatter group, I actually do have a coating on my barrel. So it's this I.95 coating. So that means that any incident light will be reflected with 95% of its initial energy along the specular path. So the coating is applied before any scatter models are applied. That's very, very important. So this coating is applied first, then we determine where the specular ray would go and what energy it would have, and then we apply our scatter model. So in this case, we had a Gaussian scatter distribution, but let's go ahead and try out our IES scatter profile. So in reflection, I'll use powdered black steel. And we'll just give it a number of rays 1. So 1 input ray will equal 1 scattered ray. Okay. And then if we want to do an analysis of how changing that scatter profile affects our system, we can run a ray trace and look at our output on the detector. When I am in mixed mode, you'll notice that I have a lot of the sequential features available to me. I don't have the same menu structure. So I need to go over to this NSC ray tracing group in order to perform my ray trace. I do want to split and scatter my rays. And then let's take a look at our output. So under NSC ray tracing, I'm going to open up my detector viewer. Okay, so on my detector viewer, I'm just going to make this a little bigger here. We can see I'm getting 1.2 e to the negative 5 watts of energy on my detector and 22,000 total hits. So 22,000 ray segments ended up intersecting my detector. And my initial launched energy I can find in that source ellipse description. So I initially launched 1 watt of power. This is often done for kind of a relative scale. So we can tell 1.27 e to the negative 5 out of 1 was found on our detector. So that is our ISX model. If instead, let's go ahead and keep that. I'm going to clone my window and then lock one of them so that it won't change and I can use it for comparison. So now if I go back into my properties and I reset that Gaussian distribution, so scatter fraction of 1, all of my rays will scatter. Now if I take a look at my output, and so I need to retrace my rays. We still see about 22,000 hits on our detector, and we have 1 e to the negative 5 watts of energy when compared to our powdered black steel model, which gave us a little more. So you can see there's some importance to picking your model. The powdered black steel does have some, because it's an ISX model, it does have some corresponding energy information within it. So in other words, we have TES values, which are total integrated scatter values. So if we know that we have 1 unit of input power, we measure how much is output into the scattering. whereas the Gaussian model is relying solely on that coding in order to provide that information. If you do have measured data for a source, we have a few options available as well. So when it comes to sources, the best pick is a radiant source model, and that is available again in a library for download within OpticStudio. And these are photometric measurements of lamps, LEDs, and other light sources. And then other options available are IES or LDT files, that's IESNA or ILLUMDAT type files. And these are standardized formats that measure far field only data. So when we say far field, what that really means is that there's no spatial information about where light is coming from. It's pretty much assumed that you're working far enough away from your source that it can be approximated as a point source. So all of the light's going to start from an infinitely small point, but then it has data about the angular distribution of where light goes. So both IES and LDT work really well for this. These are also really, really common file types that you'll find from manufacturers. So a lot of manufacturers will not have what we call near field data, which is what the radiant source models are, where we can actually figure out not only where light is going in space, but where it came from in space as well. So we get some spread of where light's distributed in X and Y and Z for the ray origins, as well as the angular distribution of where light goes. So IES and LDT, those first two, are really common for manufacturers because it's pretty easy to create those file types if all you have is a photometric sensor that you can move in the far field far away from your source. A few other options would be a DLL. So if you can describe how your rays should be launched as a function of space and angle, then you can write a DLL. And then the SDF or DAT file. So this is called a source file, and we'll talk about that one more, but it's also very valuable. Okay. So the radiant source models, again, these are measured by radiant vision systems. These are essentially a series of images of a source as it's rotated through different angles. So the picture that's captured at each interval captures how much light is coming within a certain solid angle in a certain direction out of the source. And then because it's a 2D image of the source, we can also see where light originated from in X, Y, and Z space. So once you download one of these sources, in order to use it, you'll actually convert it into an SDF type source file. I don't have a good example of a source file. So source files are extremely valuable because unlike the IES or LDT file types, they actually do contain both the starting location of rays and the angular distribution of the rays. The drawback is that an SDF file doesn't contain any sort of function or theme information. It contains an actual list of individual rays. So from that RSMX, we then look at the data as it's distributed, and we use a Monte Carlo algorithm to generate a specific number of rays for you to use in your analysis. So the reason that a radiant source model is more powerful than an SDF file is that you can generate any number of rays within your set. So it's often advised to start with a small number of rays as you're setting up your system and getting used to using it. And then you can export larger and larger ray sets to get a better and better approximation to the true distribution at that source. We do still have a catalog of IES source models as well, although as I mentioned, many of these can be found very easily from manufacturer websites directly. So both of these libraries are available within OpticStudio, and I'll again show you where you can find that. So if you go to your Libraries tab, we have our Radiant Source Models, so we can download, view, or generate rays. And then we also have our IES Source Models. So again, you can download here. We do have a couple tools and analyses that are available for viewing source information. So much like scattering, one of the easiest ways to view what your source is doing is to just set up a very simple system with a detector. But we do have tools that are somewhat analogous to the scatter function viewer and the scatter polar plot. So with sources, we have a source directivity viewer. And if you're familiar with lighting data sheets, this might look somewhat familiar. It essentially shows the amount of energy in terms of the distance from the center point here. So that's an energy scale, and then the directionality of the light coming from the source. So we can see pretty much zero energy is going directly backwards from this source. The majority, or the peak, would be coming out straight ahead, and then there is some distribution that falls off in energy as you go from straight ahead to that directly behind angle. And then we also have a source polar viewer. So again, very similar to the way that a polar detector would show information. So it will show a concentration of energy relative to some angular position from the source. So this center point would be straight out in front of the source, however it happens to be oriented. And then we can see that fall off in this case. So what do you do when you need measured source or scatter data, but you maybe don't have it? So the first thing you can do is you can look for a corresponding data set in one of the OpticStudio libraries. Now the data sets are only available for download in premium versions, but you can look through the catalogs and see what's available within professional. You can't in standard just because you don't have access to the entire non-sequential sector, which is where that tool resides. But inside professional, you can see the full list of available data items. You can also check the manufacturer's website for downloads. It's really not uncommon. A lot of the time you can at least find a data sheet, and that data sheet may show you some sort of directivity information. It may give you some generic scatter output, or like a picture of what the scatter output would look like. So oftentimes, even if you can find a data sheet, that would help, because then you can use some of those methods we talked about for approximating sources or scattering profiles. And then sometimes they'll actually have downloads directly available for BSDF files or SDF or DAT, those source files. You can also build a data set using the SDF source files or IES or LDT files. For scattering, you can build your data set using BSDF or ABg. So depending on how much data you have and how much time you're willing to put into it, BSDF and SDF are both the top pick, and then IESNA Illum sources are kind of similar to ABg Scattering in that they'll be a pretty good approximation, but they may not be 100% accurate in every case. And then the last option would be to have your source or scattering sample measured professionally, so by one of the companies who has measurement tools, and then they can usually provide you with data in a ready for OpticStudio format. Around to field some of those, and feel free to fill them in. You should see a little text bubble associated with the GoToWebinar application, so you can submit your questions that way, and we'll just take a sampling of them and answer them for the next few minutes.
So we do have a few questions that have come in. Question number one was, what is the best built-in scatter model for a ground glass surface where rays are scattered both into the material and out of the material? And I think that most of the time, what I've seen commonly used in that scenario would be a Lambertian scatter profile. And when you apply the Lambertian scatter profile, in order to make sure that rays will scatter both in reflection and transmission at a volume interface, if you have ray splitting enabled and some portion of the energy would be reflected and some portion would be transmitted, then essentially what OpticStudio does is it first calculates the specular ray paths. So if 20% of your energy was going to be reflected and 80% would be transmitted, it calculates the energy and orientation of those ray vectors, and then we apply the Lambertian scatter model to scatter about that specular ray path in each case. So we do actually apply the scattering both in reflection and transmission at interfaces that have both of those. With certain scatter models, you do need to apply those settings separately. So for example, like the BSDF scatter type will actually ask you for a BSDF profile to use in reflection and a different or same BSDF profile to use in transmission. And that's because with some of the measured scatter behavior, you could actually see differing behavior in reflection versus transmission. So we allow application of different scatter profiles in those two instances. We also have another question about what ticking the thin window scattering box does. That should be in your System Explorer. The thin window scattering, I don't have the definition off the top of my head, so it would be best to reference the help files, which I don't have in front of me, but I believe that what that does is if you enable thin window scattering, then we are trying to calculate, oh no, wait, that's simple ray splitting. Oh, I'm thinking of the wrong thing. That would be a good one to look in the help files for, but I don't have a definition for that one off the top of my head, actually. Okay. Is it possible to combine a Lambertian and an ABg scatter model? I think probably, though I don't necessarily have a 100% answer to that question. I think what you could do in that case, because you can combine multiple ABg scatter models into a single scatter behavior or a single scatter function, So probably what you would do in that case is try to find the ABg coefficients that you could use to best model a Lambertian distribution, and then you could combine that with any other ABg model. But I've never tried to do that myself, so I don't necessarily know what those coefficients would be, or if there are such coefficients that could mimic a Lambertian distribution. Alternatively, I mean, if that doesn't work, there are some other workarounds you could consider. I haven't really thought through them fully, but it could be something like having two objects that are extremely similar in size, one slightly inside the other. And one interface would have a Lambertian and the other interface would have the ABg scatter profile. So there could be some risk there in terms of, you know, getting rays that TIR between the two, or I guess that bounce back and forth between the two. They probably wouldn't TIR because you'd want them to be made of the same material. So I'd have to think through that one, but there's probably some workarounds that we could make work for that. And then I guess the final option for combining a Lambertian and an ABg scatter model would be to essentially to do some mathematical modeling of how much scatter goes in each polar and azimuthal angular direction relative to the specular ray, and then you could sum those two or average those two scatter profiles and create a BSDF file that you could use in its place. And then someone asked if I could talk about how we blocked the specular rays. So that is in reference to that ABg scatter sample file, which is included in your installation of OpticStudio. So essentially, some scatter profiles will have a very high specular component and then very low kind of haze outside of the specular. And in order to make it easier to see that sort of haze behavior and measure it, it can be convenient to just block the specular path. There are two ways to do it. Within the sample file, we actually created a second very small detector that was set to absorb. And it's small enough that it really only blocks like 1 pixel's worth of the regular detector at the location where the specular ray would hit. So we're just essentially putting a very small blocking element so that those specular rays can't reach the main detector. The other option is actually you can use filter strings to accomplish that as well. So when you're looking at your detector data in your detector viewer, or if you have saved your ray trace, so when you run the ray trace, there's an option there to save rays, and it saves to a ZRD type file. Once you have that ZRD, you can also filter in your layout plots. And we have a whole section in the help file that's titled the filter string. So if you search those words, you'll see all available filters. And there are filters available to say you could essentially filter for rays that did not scatter. Okay. I'll wait a minute to see if there are any other questions that come in. If you do have questions that we're not able to answer during this Q&A session, you could feel free to email support, and the address for that would be support@zmax.com. I'm sorry if I missed your question. Some of these are a little more specific than I think I could answer right now. We may need to take a look at your file if you've done something specific that you'd like help on. So do feel free to email us, support@zmax.com, if you have a system-specific question. Okay. Well, it looks like that's all of our questions for the moment. Again, if you do have any additional questions, feel free to contact our support team, support@zmax.com, and make sure to include your license number. You do need to be under active support. And thank you very much for attending. We appreciate your time.